Okay, so let's get started. The topic for today is data centers, as you all know. Just a few announcements before that final exam. I think you all know this, just wanted to say it one more time. April 30th, details on Piazza, or soon to be on Piazza. One additional note, the finals review material, which was scheduled for Tuesday, we won't have a live Zoom lecture. Instead, Murphy and I are going to release independent video recordings that are going to cover the lectures that we've covered. We're going to focus on lectures since the midterm. And so also for the final is going to be based primarily on the material that's happened, that we've covered since the midterm. And so that's what the review is going to focus on. Scott Schenker's lectures are still at the same time, live Zoom lecture, April 23rd and 28th. Do attend. It's a treat that we managed to get him. So let's all do him the courtesy of turning up and being engaged. And that was it in terms of announcements. So let's get started. Data centers, everyone, all of you know what data centers are, of course, or at least we have our own idea of what it is. If you look up a place like Wikipedia or something, it'll tell you that a data center is computing infrastructure in one physical location, shared by multiple users and applications. And that's actually a pretty good definition of what a data center is. It is, though, a pretty broad definition in the sense that if you follow this definition, data centers go way back. You could go back to the very first computer, the ENIAC in the 1940s, and it was in one location. It was shared by multiple users and applications. It was actually one computer. This entire room is one computer. It was also the only computer that everyone had to use. And so that's pretty different from what we currently think of as data centers. But the natural evolution does actually start from kind of this notion of a machine room or a computing room. This picture, of course, changed radically over the years. I would say the biggest impact, the biggest reason was the development of the personal computer or the microprocessor. And that, in effect, led to, rather than building one room with a giant computer, everyone was going out and buying a bunch of these personal computers and building their own machine room. Right? So this is a machine room, a set of servers or computers that service a small group. We tend to think of this as ancient, but actually if you walk through Soda Hall, you'll find pretty much on every floor has its own machine room. And then the natural evolution from there was to something that today we would call a private data center, which is just a big machine room. And so again, we talk mostly about clouds and Googles and Microsofts, but these private data centers are actually ubiquitous. And if you added up all the machines in all of these private data centers, they probably, I would guess, outnumber or equal that of the cloud providers. So Berkeley, for example, has a 10,000 square foot location on Hearst Avenue that is Berkeley's private data center. Pretty much every enterprise out there, even today, does have a private data center. But that said and done, when we talk about data centers today, we tend to talk about what people would call nowadays these hyperscale data centers. So it's one location or set of locations that have millions of servers that are reused not just by one enterprise or one company, but in the case of cloud computing, by pretty much anyone that wants to run any application on the cloud. And so our context when we're talking in this class, I want you to just have it in your head that we're really focusing on these modern hyperscale data centers. If you had to talk about a private enterprise data center, I probably wouldn't give the same lecture. So just keep in mind that our context is the Googles and the Azures and the Alibabas of the world. And you could do an entire semester, in fact, certain universities do, just talking about cloud networking and data center networking. We're going to do one lecture. And so the theme really, or what I want us to focus on, is how and why networking in data centers is different from everything that we've talked about all semester long. And so think of it as I want you to get the high order bits on how things change and why they change. We're not going to do a super deep dive on any one aspect of data center networking. But if you're interested, I'd encourage you, come take the graduate networking course. We do much more data center networking at the graduate course level. Okay, so with that plan for this lecture, we're going to just start by highlighting these unique characteristics of data center networks. And then the aspects I'm going to go deeper in on is, one is the kind of the design of these networks, like what is the topology, how do you do addressing and routing, and then this question of congestion control and transport if we have time. And again, the focus is going to be on how we approach these questions differently in this context of data centers. Okay, so with that, how are data center networks different from the ones we've talked about so far? Any thoughts, just quick thoughts at a very high level?
Well, I mean, you can control the entire thing yourself, right? Like, I mean, or like the company within their data center, they can control the network. They can probably run their own, like, internal protocols that you're not going to see out on the internet, right?
So single global control, a huge impact. And that's a theme we're going to be coming back to repeatedly. That's one. I actually had only 4. There are lots of little differences, but I thought 4 that really stand out. If someone wants to chime in, jump on the chat channel, otherwise I was going to keep going. First is sort of scale in one location. It wouldn't be correct to just say scale, right? Very hard to beat the scale of the internet. The internet is huge in scale. But this idea that you can have hundreds of thousands or almost 1 million in some case servers in one location or endpoints in one location is pretty unique to these kinds of hyperscale data centers. Administered by a single organization, what Mark just brought up. The fact that you as a single organization have control, both that you can sort of implement centralized policy and central control, but also that you control both the network and the end host. And I say to varying degrees here because this is slightly different depending on whether your own data center infrastructure. So what I mean by that is Google's infrastructure that they use to support Gmail and search and so on, and YouTube, versus you're supporting a cloud infrastructure that other customers will come and run on. In all cases, you control the network. If you're building out your own infrastructure, you completely control the end hosts as well. What I mean by that is you control the network interface cards, you control the operating system, the version of the operating system. If you choose to change your TCP stack, you can go ahead and do so. You can do all of that as a single organization with one decision maker in the context of a data center. If you're in a cloud, in the end host context, you still do control kind of the lower layers of the stack. So you control the hypervisor, you control the network interface cards, but the guest OS within a VM may be outside of your control. I mean, it is out of your control. The other form of control that's really unique to this context is you have control over the placement of traffic sources and sinks. If you think of a normal internet ISP like Verizon, let's say, they don't have the option of saying, oh, I'm going to take the YouTube stream from this house and transfer it to the neighbor. That just doesn't make sense. But in a data center context, you can do that. That's also incredibly powerful because you're effectively controlling where traffic is coming from or going to. The third point I had is that there's much, much less heterogeneity. So if you go back to the very first lecture when we talked about the internet, we said it was remarkable for its heterogeneity. You have pacemakers that are end hosts, you have cars that may be end hosts, you might have these supercomputers that are end hosts. By and large in a data center, you kind of have servers. And often it's not just servers, it's maybe just the current generation and the previous generation. That you upgrade your servers every 3 or 4 years. So you don't have all these problems that come from having equipment that's 40 years old, equipment that varies in power and speed and capacity and so on. Also much less heterogeneity in terms of round trip times, right? You're staying within one location. So you don't have underwater links and satellite links. Much less heterogeneity in terms of technology, right? You don't have this mix of not just cellular and DSL and fiber optics, but like 5 generations of cellular technology and so on. So in general, you can actually design around having some notion of bounded heterogeneity. And then the last one was much more emphasis on performance. Again, going back to when we started this class, we talked about the listing in Clark's papers of what the goals for the internet were. When they were designing the internet, what were their key goals? And if you remember, performance was actually just not on that list. They had efficiency somewhere in the middle of the list of priorities, but actually like minimizing latency, maximizing throughput is sort of not the most important thing designers worried about. In the data center context, this is critical. This is how a data center provider differentiates themselves from their competition. Every millisecond counts, every half a millisecond counts, and we're going to get back to that in a bit. So that was kind of my main list of what I would say are really the differentiators that matter. Any questions on this before I move on? Okay, so then moving on. Let's now start talking about how those differences are going to lead us to slightly different choices. And let's start with just infrastructure, like what actually does a data center look like and how do you build one? Before I go forward, the two people I wanted to highlight that really, I think actually remarkably, all of the material in this slide deck derives from work that they did. So I just wanted to call them out. One is Amin Vedat. He was a Berkeley EECS undergrad, also got his PhD here, then moved on to the faculty at UC San Diego. And when he was on sabbatical, he spent his sabbatical time at Google. And this was, I think, in like 2004 or 2005, and really started learning about how they were building their clusters and what the networking needs were and so on. And he went back to UC San Diego after that sabbatical and with his students worked on really what has become the blueprint for how we build these large data centers. He so hugely influential. Google did eventually manage to entice him to leave UC San Diego and join Google full-time. So he's now at Google and he actually runs all of system infrastructure at Google. So not just the networking, but also virtualization, servers, and so on. So really just an industry leader in terms of how data centers get done. The other name that belongs on this list is Albert Greenberg. He, not Cal, but an East Coaster for the most part of his life. But he spent most of his career actually at AT&T Labs as a researcher at AT&T. And again, did a lot of seminal work there. We talked about Gao Rexford. He was, both Li Gao and Jen Rexford at the time were in his group at AT&T, and he was really like the mentor to them. And he had a lot of seminal, really creative ideas around how people should be building networks that he worked on when he was a researcher at AT&T. And Scott will probably talk about this when he talks about SDN, because in many ways that work, you could almost view it as a precursor to SDN. But after spending decades at AT&T, he kind of got frustrated at being there. So AT&T is a very conservative, old style company. And the research group, they had all these great ideas that they could do that weren't getting picked up and put into practice. So he moved to Microsoft Research and like Amin started getting exposed to very early days of data centers. And like Amin built out almost, it's funny, the work came out at almost the same time. They both kind of had the same idea, expressed slightly differently. But so that also has become a blueprint for how industry does data center networking. He now runs all of Azure networking. So again, they've remained very influential and active in how data centers have evolved. With that, what does a data center network look like? So let's just start very small, go bottom up. We have a bunch of servers. That's our compute nodes. Every one of the servers is connected to a top of rack switch. So this is a pretty, typically not that expensive switch. The core chip that goes into one of these switches is like $200 or something. And then you have these links. So that's a server rack. And we have these links connecting every server from its network interface card up to a top of rack switch. So 10 gigabits per second is pretty standard, maybe even low end. Today it's probably 40 gigabits per second. I'm going to be talking about this as the server's access link. And when I talk about a server that's generating traffic at line rate, I mean it's generating at that limit or the rate of its access link. So today you can think of it as 10 gig or maybe 40 gig. Okay, so that's our server rack. And in a data center, we just have lots and lots of these racks. Just to give you a sense of scale, so let's say that a typical building or data center location would have, say, 200,000 servers. And you'd have maybe 50 servers in a rack. Okay, so that should give you an idea of, you'd have thousands of these racks in one place. And we want to interconnect these thousands of racks or these kind of order 100,000 servers That's kind of what we're pushing for. And that's standard today. So this is not even being ambitious. That's just representative of current state. And so the central question we're going to be talking about is really how do you network these racks, right? And the goal here, the thinking has always been to be very kind of application developer friendly, in the sense that we want application developers to be able to write all of these big data distributed applications without ever worrying about the network coming in the way. So they should never have to work around limits of the network, right? So that's kind of the goal that's driving all of this. And so before we go into how we do this, we should talk a little bit about what the traffic looks like and what the traffic requirements are. Okay. So let's start very high level. If you had a simple web search, what does this look like to a data center? You ship your request off to some server in the data center. And that server is then going to farm off a whole bunch of queries. It's maybe querying the index for that search engine. It's maybe querying the user profile. Maybe it's generating ads to respond and so on. And then it's shipping a response back. What matters for our context, or what's important, is a distinction between traffic that's coming into the data center from the outside world and the traffic that's within the data center. And this was sort of a very simple toy example. How complex are these kinds of what we call partition aggregate queries, where you have one request come in and it kind of farms out recursively all of these internal requests. This is just one stat from a study published by Facebook, where they say that for one popular page that's being loaded, so you're getting one request from the outside world, you might be generating an average of 521 memcached lookups. So this is lookups on their internal key value store. Okay, so all of those arrows coming out inside, on average 500 of them. And they actually go on to talk about how in many cases it could be like 2,000 or so. A different type of workload that we'll talk about often is not necessarily something that's in response to a user request, but could just be analytics on the data that's stored within the cloud. Right? So mining your data for insights and so on, running MapReduce, Spark, Hadoop, and so on. And again, in the context of those workloads, all of that request response traffic is happening within the data center. Okay, so where I'm going with this, so if we talk about data center traffic, you'll typically hear people talk about north-south traffic. This is traffic that's going between the data center and the outside world. Okay, so this is like the user sending in their request to the data center. And then we talk about east-west traffic. This is traffic between servers within the data center. And by all accounts and everything we've heard from all data center operators, east-west traffic is several orders of magnitude larger than north-south traffic. And so that's really going to be our focus, is focusing on how we support this east-west traffic. Okay. Is it a big deal, or what are we talking about in terms of volumes? The volume of traffic is large and growing. So this is a graph showing the aggregate traffic on the y-axis with time on the x-axis. It's normalized. Typically, most of these data centers, when they release data, they never tell you what the absolute numbers are, unfortunately. So they'll normalize it so you can see a trend. And so the takeaway here is, if you look at this, there's a 50x growth in traffic over a period of about 6 years. So that's pretty remarkable. That's way faster than Moore's law even. And so we have to support a huge amount of this east-west traffic. And this east-west traffic is growing quickly. And we can't just hope to deploy bigger links or faster routers. And so that becomes our central question, is how do we support these high volumes of east-west traffic? And our goal here is, again, ideally, informally, if you think about it, I want every server in the data center to be able to talk to any other server in the data center at its full link rate. If we can support this, then that's a great model for application developers, right? They're on a server, they have a 10 gig link, they can just talk to any other server. It really simplifies distributed programming. Slightly more formally, what we're saying is that we want a network with high bisection bandwidth. Is this a term that's familiar to people? Okay, so let's go over what bisection bandwidth is. So bisection bandwidth is actually a pretty simple idea. It's you take a graph. It's a formal definition from graph theory. It's you take a graph and you want to partition the graph into two equal halves. And then you want to look at how much bandwidth there is between those two halves. And so the way we talk about it is we say you pick the minimum number of links that you must cut in the graph in order to partition that network into two equal halves. So it's like a minimum cut, but it's a minimum cut in order to get two equal halves. And then we add up the bandwidth of the links in that cut. And that's our bisection bandwidth. Okay, let me repeat that one more time. So we look for the minimum number of links that are going to partition the graph into two equal halves. And then the bandwidth of those links is our bisection bandwidth. So when we talk about full bisection bandwidth, what we're saying is that the bisection bandwidth should be such so that all the nodes in one half in one partition can talk to all the other nodes in the other partition simultaneously at full line rate. Okay, so I took n nodes in a graph, I divided it into n by 2. So each partition has n by 2. And now I'm saying the n by 2 nodes in one partition can talk to the n by 2 nodes in the other partition at the full capacity of their access link. So if I had n nodes, my bisection bandwidth, if my bisection bandwidth is n by 2 times r, then I have full bisection bandwidth. Informally, this just means any node in the left can talk to any node in the right at full line rate. Did that make sense? Would anyone like me to repeat that? Going once. Okay, so we would like to have a network that has full bisection bandwidth, because then basically it means anyone can talk to anyone at full access, at full rate, line rate. But in practice, that's incredibly expensive to do. So it's quite common to do what people will call oversubscription, which informally is just how far off are we from full bisection bandwidth. More formally, if you look at the graph literature, it's defined as the ratio of the worst case achievable bandwidth to full bisection bandwidth. So you take a certain traffic pattern between nodes in one partition to nodes in the other partition, and you'd look at actually how much traffic can they send before we have maxed out the links that are between the two partitions. That's the achievable bandwidth. We would divide that by the full bisection bandwidth. And so you'd say maybe, I'm half, which means I'm only at half of the full bisection bandwidth. So going back to, we want a network with high bisection bandwidth. Would anyone like me, was that concept clear to everyone, or should I repeat it? It's basically take the graph, take the set of endpoints, divide them into two equal partitions, and ask how much bandwidth do I have between the two partitions? And what we're aiming for is lots of bandwidth. Conceptually clear, even if the exact definitions are not? Can I get some response? Okay. Thank you. Moving on. So let's talk a little bit about how we're going to get this high bisection bandwidth. And I'm going to walk through a few design options that are clearly broken, perhaps, but I think it's useful in order to kind of set the path towards where we're trying to go. Okay. So let's start with what I'm going to call a big switch approach, which is I'm going to take every one of those racks and I'm going to connect them all to one giant switch. Okay. And this is clearly a bad idea for many reasons. One is the number of ports I'm going to have at a switch is on the order of the number of racks that I need. So just to put some numbers here, we said we would need thousands of racks. And typically, if you look at some of the switches today, they have ports that are like in the hundreds. So 1,000 is not something that's very easily achievable. Bigger problem is that the speed or the switching speed is basically order number of servers times the server access speed, right? Because we're basically connecting all the servers to this big switch, going through the top of rack switch. But if we're saying we want full bisection bandwidth, we're basically saying all servers should be able to talk to each other through this big switch. How bad is that? If we said I have 100,000 servers and they're 40 gigabits per second, we're talking about a switch that has order petabits. So petabits is 10 to the 15, right? So we're going mega, giga, tera petabits. So that's just not something we know how to build today. Terabit switches exist, petabit switches do not. And so really this approach, I'm sure it was obvious to you at the beginning, but it doesn't scale. And sort of a subtle point to make here is that even if we could build such a big switch, right? Because maybe, you know, we put a whole bunch of really smart people in a room and they figure out how to build this big switch. It would be a highly custom or non-commodity design. And that typically means that it would be a very expensive design. I want to just spend a couple of minutes talking about this notion of commodity design, because this runs through all of data center design. Right? People want commodity solutions. I think we all intuitively understand what we mean by that. In this context, typically what it would mean is that there's typically a generation of technology that is commonly available. It's widely available at a particular time. And because of that, it actually drives the cost down, right? And so, for example, today, if you said 10 gig or 40 gig is commodity, you can get a 10 gig link or 40 gig link. You can get it from, you know, hundreds of different vendors, usually not expensive because you have 100 different vendors. But on the other hand, if I said, oh, I want a switch with a 1 terabit per second link, that's not so commodity anymore. And while I can go buy it, there's probably 2 vendors that I can go get it from. And if I look typically at the dollar per bit of what is commodity technology versus the dollar per bit for what is kind of cutting edge or emerging technology, there can be a huge difference. They can be like between 2 times more expensive to 10 times more expensive for what is commodity versus not commodity. And so these data center providers really want a solution that is commodity. Another reason why commodity is building off of commodity pieces is important to them is to avoid being locked into a particular vendor. Right? If you design your data center in such a way that the only person in the entire market that can build it for you is Cisco, then if you're a Google or Microsoft or an Amazon, you don't want to be in that position, because then what if Cisco starts charging you too much? Or what if Cisco goes out of business? Then you don't have a viable plan. And so we're going to come back to this theme over and over. We want commodity designs. That was hugely influential in shaping how people design data centers. So that was a big switch. We didn't like it. What if we took another perhaps obvious topology, a tree network? And so we just built a tree of switches on top of these top of rack switches. This takes care of the problem of having this fan out of 1,000 ports that no one knows how to build. But if we just said, oh, we have all links that are the same capacity, we're clearly not going to have that bisection bandwidth, that high bisection bandwidth. If all the servers on the left-hand side decided to talk at the same time to all the servers on the right-hand side, we're going to very quickly overload that tree at the top, the node at the top, and the links at the top. Right? So this wouldn't work either. So what we might then consider is something called a fat tree. This is actually a name. I did not invent it. So a fat tree is basically a tree, but the links as you go up the tree get fatter. They get higher capacity. How high capacity should they get? If you're in graph theory land, it's whatever capacity you want in order to support whatever bisection bandwidth you want. So if you wanted full bisection bandwidth, those links at the top would very quickly get very fat. So fat that in fact we don't know how to build them, or at least not with commodity solutions. So in a fat tree, the port count problem goes away. The I'm congested at the top of the tree problem goes away. But we are left with this problem of how do I get these fat links and these high link speeds and switching capacity at the top, right? So as a logical view, what you should think is that as a logical concept, what I want to build is a fat tree. But I don't actually know how to build it in a way that's scalable or that doesn't require some kind of specialized links and specialized switches. Okay. Is this clear so far? Any questions or anything that I can repeat? Yeah, can I re-explain the fat tree? So the fat tree is exactly the same as a tree, right? With only one difference, which is that as I go up the hierarchy towards the root of the tree, at every level, the links get fatter. What do I mean by that? They just have more capacity. So let's walk through an example, right? Let's say that I had, just for simplicity, I'm going to say, let's say we had 10 servers in a rack. Okay. And each server has, so that's these within a rack here. Each server has a 10 gig link connecting it to its top of rack switch. Okay. So I have 10 servers. Each talking at 10 gig to the top of rack. And so if I didn't want to have any risk of congesting, what capacity should this link be? Do people see my cursor? The link between the top of rack and one node above it. Right? So I have 10 servers, each with a link of 10.
Yeah.
Yeah, so going up from that top of rack switch, I want this link to be 100 gigabits per second. So one link, 100 gigabits per second. That was just 10 servers times 10 gig. Now here at this switch, I had 2 of them, and this is a toy example, so it's only 2. Right? But let's say it was 2. Then this fat link over here going between the root and one level below would be 200 gigabits per second. Now, more realistically, typically, rather than just 2 racks below, I would have, let's say, 20 racks. And so actually, this would not be 200 gigabits per second. It would be 2 terabits per second. Okay, so it's just a tree topology, but the capacity of, or the speed of each link as I go up the tree is getting fatter. It's increasing in capacity. Does that make sense? Can I repeat that one more time for anyone? Okay. So we like this model, right? If I really could build a 2 terabit per second link at the root or a 20 terabit per second link at the root, this would be great because I don't have a high port count. I do have high bisection bandwidth and I'm happy. But I can't actually build those fat links. So we still need an alternative. And the alternative to that is something called a cloth network. This is actually a very, very old idea of a network. It was developed in the 1950s. People would build telephone switching networks out of this. So in this context, you know, if you look at the switch as a whole, to the left here, the input telephone lines, to the right are the output telephone lines. If you wanted to place a call from an input line to an output line, you would find a path through the cloth network and set up the connection between the 2 telephone lines. Okay, so this is a cloth network. It's basically you're building a larger switch or a larger network out of a whole bunch of smaller switches or smaller network switch elements. And so this has the theme of we want to build a large, high capacity network using small, and in our case, it's going to be commodity building blocks. Let me pause a second just to read the chat channel. Would the factory not scale because the capacity of the links depend on the situation? Absolutely. So let me go back to this. If we were in a context where, you know, these links at the bottom were 1 gigabit per second, and I only had, let's say, 100 servers. And let's say if we did the math and we said, oh, this link at the top needs to be 100 gigabits per second, then you could absolutely build a factory for that context. But our context is, we have 100,000 of these servers. So let's say we have 40 servers in a rack. And our context is that typically access links are like 10 or 40 gig. And so very quickly, this becomes hundreds of gigabits per second. This becomes terabits per second, and so on. Right, so let me look at the next question. So in this bisection model, we're saying hosts want to talk to hosts in the other partition. But how about communication within one partition? Yes, so you actually want any host to be able to talk to any other host in the network in its entirety. Usually talking about one partition to the next partition is the worst case. So if we talk about that, then all hosts can talk to each other at full line rate. Okay, so it certainly is the case that I want 2 servers in the same rack to be able to talk at their full line rate. And the top of rack switch will do that for me. So at every point, we have to ensure that any server can talk to any other server at full line rate. If we have full bisection bandwidth, we are guaranteed that basically. Because remember, bisection bandwidth is the worst case partition. Let me keep going through some of the chat questions. Yeah. Should I move on? Okay, so back to the cloth network. So why do we like the cloth network? We're going to build a high capacity switch out of a collection or an arrangement of these smaller, cheaper switches, right? So if I look at this figure and I look at one little switch here, it's a 4x4 switch. right? It has 8 ports. In the old phone network terminology, they would have called this a 4x4. And yet they've been connected together in such a way that effectively what they've built with this closed network is a 16 by 16 switch, right? So 16 inputs, 16 outputs. So in the old closed terminology, you would say you've built a 16 by 16 network using 4x4 switches. And you could go further. You could make this a 32 by 32 by just adding more of these rows and more of the links, and more rows and more stages, more columns. So you could scale this out. And so some of the important properties that you should notice here is that all of the switches have, give me just a second because my chat channel is hiding my own slide. All of the switches have the same number of ports, right? If you look at any one of these little switches in this figure, they all have 8 ports. Right? So we eliminated the problem that the giant switch had, where it had to have a port effectively for every rack. Moreover, the number of ports is actually low. In this case, it's 4x4, and I could, by combining more of these, build pretty much whatever capacity network I wanted. And the last important point is that if you look at this topology, all link speeds are the same. Right? So both these internal links, the external links, all of the links are the same speed. And if you build this kind of closed network, you can prove that it has full bisection bandwidth, or that there is configurations of closed networks where you have full bisection bandwidth. And that's kind of a result that comes in the graph theory. There are entire courses in graph theory that will talk about different ways of analyzing closed networks and so on. So that's kind of the basic idea behind a closed network. I haven't yet told you how we're going to use it for the data center, but this is conceptually the closed network. The important thing to remember is you're building a bigger switch or a bigger network out of a collection of these small, cheap switches. And the port count is the same and a constant on every one of those switches, and the link speeds are the same. So you're not scaling badly. Any questions on the idea behind closed? I don't expect you to be able to analyze a closed network or draw one on your own, but just to get the idea of what's going on here. Is this good? So quick question, is each box a switch? Yes. And so in the 1950s, this is how they built telephone networks. Each of these was a little switch, and they would build one giant telephone switching fabric by putting them together. Okay, so how are we going to use this for the data center case? So first observation is we don't actually, our context is not really that I have a set of physically different input and output lines. Instead, every server is both generating traffic and receiving traffic. So it's both an input line and an output line. So actually this right-hand side of the clause, we don't quite need it. We're going to go from the left, from input on the left, we're going to go through the clause network and go back out to another one of these left-hand side links. Okay. So this is actually called a folded clause network. Again, if you go into the graph theory. And what we're going to do is we're going to take one of these folded clause networks, and every one of those left-hand side input links is effectively a top of rack switch connecting to a switch above, right? So we're going to have a whole bunch of these racks. So conceptually, that's how we want to use a clause network. And this was exactly the proposal that Amin Vadat and his students at UC San Diego had when they were proposing how to think about future data center designs. Let me pause here for a minute. Any more questions on this notion of a clause network and how you use it in a data center? Okay, let me go forward then. So this is a picture that's, question. So which is the top of rack switch? The bottom level. So in this figure, so this figure is copied from the Amin Vadat paper. It's a little bit of a toy example. So in this figure here, the first lowest level of switches is the top of rack switch. And this is a bit of a toy example in that, every switch has 4 ports and it only has 2 servers. But this is the top of rack switch. This is what they'd call an aggregation switch and a core switch. So this is a toy example of a data center network with 16 servers. And interconnected by a folded cloth network. And let's just check that it has all of the properties we liked, right? So every one of these switches has exactly 4 ports. Every one of these links is going to be the same speed. So if the server to top of rack switch link is 10 gigabits per second, then every one of these links in this topology is going to be only 10 gigabits per second. Right? So we're not buying fancy high-speed links. And this is going to give us high bisection bandwidth. So one point I wanted to make is when you go out or talk to many people, they'll say that data centers build fat tree networks. And this is an unfortunate consequence of the confusion when this paper was published. So in this paper, what they said is that they were using the cloth network to emulate a fat tree network. And then they continued to call it a fat tree network, which logically, if you're looking at it, this is a fat tree where if you said that the root is that entire top level of switches, and then the next level in the tree is just by aggregating different numbers of switches at each level. And as you can see, the links get fatter at the top. So this is a cloth network that's emulating a fat tree. That is true. It is not exactly a fat tree network. And as Google has gone forward, they've corrected themselves and called this a cloth network. But the original paper called it a fat tree network, and that name is stuck for better or for worse. So we're going to call it a cloth network. So a question from Abhinav, is it expensive to have so many links? So here's a way to think about it, right? You can have 10 gigabit per second links, or you can have 100 gigabit per second link. And per bit, it's usually cheaper to have 10 gigabits per second link. So usually the current commodity link speed is cheaper per bit than having one high-speed link or having some advanced speed link. There's a separate question, which is maybe what you meant also by, is it expensive, which is, isn't it a pain to have so many links, just in terms of the cabling and the wiring? And we'll get to that in a minute. Does that answer the question? Okay, so let's just recap whether we're happy with this cloth network. Okay, so it equal small port counts, small low speed links, or at least not high speed links, high bisection bandwidth. If you look across any level in this topology, so starting between the servers and the top of rack, and then between any 2 successive stages of switches, you'll see that we have the same bandwidth available, whatever that is. So if we had X gigabits per second at the level connecting servers to the top of rack, we have X gigabits per second at the top level. So you can build extremely high bisection bandwidth in this way. You could also, if you chose to over provision, you could just say, okay, I'm going to take out 2 of these switches at the top level and take out all of their links. And in that case, you'd have X by 2 at the top. And so you would have oversubscribed by a factor of 2. Right? So you don't have to build a full bisection bandwidth network. It also offers you many paths between any 2 source and destination, any pair of source and destination. You have multiple paths between them. So it's also very fault tolerant, right? If one switch goes down, you can always send your traffic along a different path. So it has a lot of redundancy built into the topology. And so overall, we like this topology, right? Is any questions about why we like it or why this is a good topology to be working with? Okay, so moving on. And this is pretty much what most of the large data center providers, this is kind of the blueprint or the template they're following. There's a paper published in 2015. So this was, almost 10 years after Amit Virat's group at San Diego started working on this, that talks about all the generations of cloth topologies that they've had at Google and how they've evolved in time and how they've scaled in time and what worked and what didn't work. And so this is actually a picture from that paper showing one of their cloth topologies. If you're looking at this, and one of the questions that someone alluded to, this is a lot of links. And so, yes, in fact, how you do this wiring has turned into a problem of its own. And there's papers around how you do aggregates of cabling together. And Google, you can walk through and see their layout of cables and how they manage that. Yes, that is a downside to the fat trees. Variants of the design are common. So these are figures showing to the left is from Microsoft. This was actually Albert Greenberg's work at pretty much the same time of proposing a very similar design. The right is a 2015 paper from Facebook showing how they built their networks. And again, it has basically different variants of the clause topology. And so that's kind of the blueprint or the norm in how people are building data center topologies today. I should point out that clause topology is one in a kind of family of what people will call parallel graphs or parallel interconnects. There are these topologies that tend to have a very regular structure and that have a lot of parallel paths between any source and destination. And so there's been work looking at, is the clause topology actually the best topology from that family, or could you actually do something better? So there's a whole literature there looking at, are there better topologies? So I wouldn't say this is set in stone for the rest of time, but this is how things get done today. So recap, what we wanted was high bisection bandwidth that you could do in a cost-effective and scalable manner. This is actually a classic example of scale-out versus scale-up design. So is that a concept that you've heard before, that you've studied in CS 162 probably, or that you're familiar with, this notion of scale-out versus scale-up? Yeah, so scale-up is this, it's the kind of the old way of thinking. Scale-up design refers to, I have a component. If I want to scale it, so I want it to go faster or to be more powerful, I build a bigger version of the same thing. And that's kind of what supercomputers did for many generations, right? You build it bigger, you make it go faster, you put more memory, more CPU in it. Scale out says that the way I get more capacity is I add more of these cheap components. That's kind of scale out. And pretty much all of data centers and cloud have this notion of scale out design deeply, deeply ingrained in how they build systems. And that's actually how we build software systems as well today, right? When you build a Spark or MapReduce job, you're scaling the processing capacity of your MapReduce job by having more parallelism, by running more workers or more threads. And so this is very much in that spirit. Is that clear? Okay. So let's move on from that. So we're going to take now in our heads that clause-based topologies are how we're building the physical wiring of our data center. So now we have a topology. What are we going to do with it? And it's very important to realize that the clause-based topology means we have a physical topology that offers us high bisection bandwidth. We now have to design all the other layers of our network and actually our stack and our software to be able to exploit this bandwidth. Right? So for example, routing must exploit all the paths available between a source and a destination. Right? If we're not using all the paths, it's not very useful to us that topology was fantastic. Likewise, our transport protocol and our congestion control protocol has to be able to send traffic to fill those pipes. Otherwise, again, right, if I gave you 100 gigabit per second capacity, but you're sending at 1 gig, then not very useful. So all parts of the design above that topology have to be able to exploit it in order to actually achieve this high bisection bandwidth. And so we're going to talk about two of those aspects. One is how you do routing and addressing. And again, if time, we'll talk about congestion control. But again, the goal here, the focus is how do we make full use of that bandwidth? And I'm going to talk in each case about two design options. One is kind of a very incremental design in terms of incremental as a delta over what we had prior to data centers or to traditional solutions. And the other solution I'll talk about in each case is kind of more clean slate radical solution that has been implemented and deployed, but it's a nice example of kind of thinking out of the box in context where you can, right? In data center context, you can kind of, one of the big nice things is you have the option to design from scratch. It's a clean slate, right? You have single administrative control. You control both the end host and the network. So you can design the entire system to suit your needs. Okay, so with that, what is our incremental approach to doing routing on top of a clause-based topology? One option I'm going to say is let's just think about extending distance vector and link state. So any thoughts on how you do that? Distance vector, right? We're advertising distance to a destination, and then we pick the shortest or the neighbor with the best distance, how would you extend it to run on a clause topology? Remember, our goal is to use all the paths and all the bandwidth available. A pretty straightforward fix. Instead of just remembering and breaking ties and picking one next hop neighbor to the destination, let's just modify the algorithm to remember all the next hop neighbors that had an equally good path or an equal cost path to the destination. If I go back to this figure here, not this one, not this. Oh. If I go back and I say, let me look at this one switch over here and think of its next hop going to any destination that's orange, green, or red, it has two possibilities, right? This top switch or the next top switch. So instead of breaking a tie based on router ID or whatever, it's just going to remember both of them. That's the basic idea. So a pretty small change to distance vector, but that would allow me to remember both next hops and both paths. Is that clear? Would someone like me to repeat that? I haven't told you how we're going to use those next hops. I'm just saying if we ran distance vector on a clause topology and every switch remembered all the next hops that have an equally good cost to the destination, then we'd be good in terms of discovering routes. Did that make sense to people? Yeah. Okay, thank you. Likewise, link state, right? We ran Dijkstra's on a graph and we said, and we have this tie breaking rule, we picked a shortest path to each destination. You could as equally just compute all the shortest paths to each destination and then keep all the next hops that have that equal cost. Right, so the notion of equal cost here, the only thing that's changed in the clause topology is that I have multiple next hop nodes that all have the same. I always have multiple next hop nodes that have the same cost to a destination. So I'm going to remember all of those next hops now. And so then the only remaining question really is how do you spread traffic across the next hops? And again, the two options here, one is you do per packet load balancing. Right? So every time a packet comes in, I pick the next hop either at random or in some round robin fashion from the set of possible next hops. Right? Is that clear? So a question here on the chat, if a route is slightly costlier than the best one, but better distributes the load, would we never consider it? In this solution that I've described to you, no, we are only taking neighbors that advertise the same cost. So it's equal cost. I'm not sure what you meant by, but better distributes the load. So you mean use even other neighbors that have a slightly longer path in order to do better load balancing? Was that what you had in mind? Yeah, so in theory, you could do that. In practice, in a clause topology, you have so many neighbors that have the same cost path that you're actually getting pretty good load balancing without even considering that. But as a general idea, yeah, absolutely, you could do that. If you do that, then you have to make sure you don't end up with loops. Right? You don't want, you sent it to someone that then sends it. You want to make sure that at every point, your cost is decreasing and so you're not looping. But that aside, yes, you could certainly think of doing that. Okay, so let's say we were doing this per packet load balancing. We do a very good job of spreading traffic across the multiple paths. The downside to this approach is you could make TCP very unhappy. Right? So one way you could make TCP very unhappy is just reordering. So if I had 5 next hop neighbors and I'm sending packets, 1, 2, 3, 4, 5 on 5 different links, they're going to follow different paths through the network. And for minor differences in queuing along those paths or any number of reasons, the receiver could get those packets out of order. So it could get them like 5, 4, 3, 2, 1. And what is it going to do when it gets, instead of getting packets in order 1, 2, 3, 4, 5, it's going to get them in order 5, 4, 3, 2, 1. What would happen with TCP? So at the sender, what would you get? You would get basically duplicate ACKs. Right? You would get duplicate ACKs until the right packet arrives, which means you would enter fast retransmit, you would cut your congestion window, you would cut your rate. This would not work so well. More generally, there's just a number of reasons why TCP is really fundamentally not designed to run on top of multiple parallel paths. For example, you have one round trip time estimation, but what is a round trip time estimate when you actually have 5 paths instead of 1 path? You ought to have 5 different round trip time estimates. Another way in which it's broken is, if you think about it, every time you have a packet drop, you cut your rate in half. But you actually dropped a packet along 1 out of your 5 paths. So you didn't need to cut your rate in half. That was excessive because the other 4 paths did not drop any packets. So there's just lots of reasons why TCP is really not designed for routing over or having packets transferred over multiple parallel paths. There is a standard called multipath TCP that has emerged just exactly to address this problem of, if I have 3 paths, 3 parallel paths between a sender and a receiver, how do I run TCP on top of those 3 parallel paths? But we're not going to go into multipath TCP. Is the problem clear about why TCP running on top of multiple parallel paths is not a great idea? Right. So how would you fix this? The simple fix, and this is the industry standard thing to do, is to not do per packet load balancing and instead do per flow load balancing. And so what this says is, you pick one next hop for a given flow, and all packets from that flow are going to follow the same path. So we're not going to get this perfect, spreading all of your traffic packets in a flow across multiple links. Instead, the load balancing we're getting is by balancing flows across different paths. So different flows, even if I took one source and destination pair, if there are 10 flows between them, those different flows might go on different paths, but within any given flow, we're following one path. Okay, how would you do this? A simple and standard way to do this is you hash the flow 5 tuples. So when a packet comes in, you take the source destination IP address, port numbers, and protocol, and you hash it to pick one of your next hop options. And then all packets in that flow are going to go over the same next hop. This is actually, so if you use this, the traffic is not as perfectly load balanced as with per packet load balancing, but TCP remains happy and you're still spreading traffic at the level of flows. So this is basically the idea behind a protocol called equal cost multipath forwarding, which basically spreads flows across equal cost next hop neighbors. So is this clear? What we're going to do in this first design option, we're going to take a clause, run a distance vector link state with some extensions, and then we're going to do something like per flow load balancing to actually forward the traffic across all of those multiple paths. Any questions before I move on? Is the path deterministic? For a given flow, yes. Right. If I have 4 next hop neighbors and I'm doing this hash-based selection of the next hop, then I'm always going to pick the next hop. Why use TCP? Couldn't you make certain reliability guarantees about the network since you control it? We're going back to the end-to-end argument though here. Yes, you could try and make your network as reliable as possible. If you wanted it to be absolutely loss-free, normal Ethernet, for example, wouldn't give you that. And so you still do want your end host protocol to implement reliability. Does it actually have to use TCP per se? You're absolutely right, it doesn't have to, but at least if we're building out of commodity Ethernet links, you do need some form of reliability protocol at the end host. That said, there are certain networks that InfiniBand is a network technology that guarantees you that every link is lossless. And so there are data centers that use InfiniBand and they use different end host software for that. They don't use TCP. All right, so let me recap this design possibility. So the possibility is we extend distance vector link state. This is certainly doable, and it's doable with relatively incremental modifications. Nonetheless, this is not the most scalable solution. And so if you think about both distance vector and link state, how they scale, you have per destination route advertisements. Here you potentially have 100,000 plus destinations. And you have link state advertisements for every single link. And as we drew that fat tree out, you saw there's a large number of links. So this is certainly doable. It's not the most scalable. It's also not widely done. To the extent that people do things like this, they usually partition that fat tree into sub-regions and then run a protocol within that sub-region. The early days of data centers, people actually tried to do this. At this point, I think very few, or as far as I know, none of the major cloud providers or data center providers do this. So can we do better, right? I said the other possibility is to just think from scratch. If you were to do this, ignore distance vector, link state, and what we've learned before. Any thoughts on how you would do addressing and routing? I have a hint here in the naming of the option. But any thoughts on how you'd do things differently if you were building on a closed network? Right. So the idea I'm going to propose, and this was what Vedant's original paper proposed, was that we let a node's address, we address a node, or we pick an IP address such that it exactly captures its exact location in the topology. And so since the topology is regular, meaning I know it's a closed topology, I know exactly what the topology is because I built it, the address is going to tell me exactly where the node is. So let me explain that with an example, and then we'll go back to that statement and see if we understand it. So let's say that this was my topology. And I, as a network designer, I know that this is the topology I've built. I'm now going to hand out IP addresses to every one of these servers. So I have 16 of them in a manner that reflects where that server is in the topology. So this is really just a form of hierarchical addressing. So for example, I say all the blue servers are 10.0 something, 10.1 for orange, 10.2 for the greens, 10.3 for the reds. And then I do this repeatedly, right? So within the blues, I say the two on the left are 10.0.0, the ones on the right are 10.0.1. And I continue to do this. So now if I tell you, where is node 10.2.0.1, right? You as a network designer, you know exactly where that server is in your topology. You didn't need to discover it or have a dynamic advertisement protocol in order to discover it. You knew the topology, you know how you did addressing. So you know that 10.2 means it's in this green portion. 10.2.0 means you went in the first left-hand pair. And 10.2.0.1 means it's this particular node here. Right. So think about what we've done here, right? We know the topology. We assigned addresses to map exactly to that topology. And so based on that, we also know what the routing tables need to look like, right? So if I take this switch or router over here, and I'm just, for convenience, labeling the ports to be 1, 2, 3, 4, we would say that anything that's 10.0, you go left down to this blue switch. Anything that's 10.1, you go over port number 2. 10.2, you go over port number 3, and so on. Is this clear? Would anyone like me to repeat this? Is what I did here clear? Okay, so let me pick another switch here just to make sure we're following what's going on here. Again, if I said the ports are 1, 2, 3, 4, I would say anything that's 10.0.0, go out port 1. Anything that's 10.0.1, go out port 2. Anything else, go to port 3 or port 4, and I don't really care which it is. And then, you could implement some load balancing scheme. The original Vedant paper actually had a nice load balancing scheme looking at the suffix of an address, but it's basically some load balancing scheme to pick between 3 or 4. Let's assume it's ECMP or something. Okay, so that's the routing table at the switch. If I look at a switch at the next level, again, 10.0.0.0 is port 1. 10.0.1.1 is port, sorry, and I got that wrong. It should have been 10.0.0.1 is port 2, and anything else is port 3 or port 4. So what have I done effectively? I knew the topology. I knew how I assigned addresses. You could imagine writing a simple program that took in a few parameters like, here's the number of servers, here's the number of stages in your closed network, here's the degree or how many links each switch has. And you had a little program that then generated what each of these routing tables looked like. You could just go in and directly program the routing table at every one of those switches. And you didn't have to discover where servers were, or you didn't have to discover what their addresses were. So now does this idea of what we've done, the basic idea that we're going to address nodes so that it precisely tells me where in the topology it is that clear? Yep, going once. So a few implications of this design approach. The number of routing entries at every one of these switches is just the number of ports. It's not order number of servers. I have perfect aggregation. I know exactly which set of addresses hang off of each port because I assigned those addresses in a way that made that happen. I didn't really need a dynamic or distributed route computation. I ignored one thing around failures, but let's get back to that. Right? I could just generate the routing tables from knowledge of the topology. It's like I hard-coded the topology and the addresses. It does require careful addressing. If you give a server the wrong address, then that misconfiguration would be really, really bad in this case. What I ignored here was link failures. But again, if I had a link failure, you could imagine recalculating the routing tables and updating them. Did this overall approach make sense to people? So it's sort of an example of what's possible when you get to design the entire system from scratch. Right? So it's scalable. It's using all the parts. So it's doing good load balancing. It's resilient. Any questions on this? What is meant by the topology being regular? So it's typically regular graphs or regular topologies means that it has a well-defined structure. So we're saying every node has a fan out of X, so it has so many ports, and we're telling exactly which other nodes that node is connected to. So there's no randomness, basically. And it's kind of what we're exploiting there is, because there's no randomness, I don't need to go around discovering which server is where and which address is where and which link is where. I just know it because that topology is regular. So examples of topologies that are regular would be a square, a cube, a torus, a mesh. Any of those would be regular. A random graph is not regular. Okay. And again, this is exploiting the fact that you get to design your data center. This was not an option on the internet where everyone had their own networks even before the internet got formed, and every provider is evolving their topology independently, and you have no idea how they're evolving their topology. In this case, we know the topology, and that can be a game changer in how we do addressing and routing. So just to recap, topology, routing, addressing, what we wanted when we started was a scalable solution to achieving high bisection bandwidth. We did this by having a topology that was building a high capacity network, or what people will call a fabric, from a collection of these smaller switches. And the topology we were using was a close topology. It's an example for scale out approach where you have multiple parallel paths between every source and destination, and you get high capacity that way. And then we designed routing and forwarding solutions that actually exploit that multipath, those multiple paths. Any questions before I move on from routing and forwarding? Okay, anyone would like me to repeat? Because from this point on, most of what I had to say, I think, is sort of optional. Okay, so then let's move on. So now let's think about congestion control and transport. And the big problem we're going to have in data centers is queuing delay. And so let me work through a simple back of the envelope to highlight why queuing delay matters in data centers. So if you remember going way back, we said packet delay, end-to-end packet delay is a combination of transmission delay, how much time it takes me to put that packet on a wire, propagation delay, which is the time it takes for that packet to travel, kind of speed of light limited, across the wire. And then queuing delay, this is if I arrive at a switch or router and there are other packets in the queue, I have to wait for them to be transmitted, and that gives me queuing delay. To put some numbers here, let's say we had a 10 gig link and a 1,000 byte packet, okay, so 8,000 bits. Your transmission delay for one packet at one hop, if you divide 8,000 bits by 10 gig, It's 0.8 microseconds. That's how long it takes me to transmit one packet at one switch. If we now said that on average, I have a queue size of 10 packets, so that there are 10 packets in my queue, right? So what I'm saying is when a packet arrives, I can't just be immediately transmitted out. I have to wait for, on average, 10 other packets to be transmitted. Then at every hop, my queuing delay would be the average number of packets in that queue times the transmission delay for each packet, right? Because I have to wait for every packet that's in front of me in the queue to get transmitted. So if we said I have 10 packets and it takes me 0.8 microseconds to transmit one of them, I have to wait for about 8 microseconds. This is at one switch. If we said that at every hop, so I have to do this at every hop, and let's say we said we have 5 hops. And so my queuing delay is now 5 times that 8 microseconds. So it's 40 microseconds. Okay. Everyone with me so far on how in this example, we have 40 microseconds on average of queuing delay? Yeah. Should I repeat that? Okay, I'm going to continue. So in the context we've been talking about so far on the internet, the propagation delay, if you take the speed of light and you do calculations and you do measurements of the typical propagation delays on the internet, we're talking orders tens or hundreds of milliseconds. Right? So East Coast to West Coast, maybe you're like 70, 80 milliseconds and so on. And so if you said that you incurred a queuing delay of 40 microseconds and a propagation delay of say 100 milliseconds, no one would care about the queuing delay. It's in the noise, right? It's not the dominant factor in what's causing the packet delay you experience. But in a data center, between two data servers within a data center, the propagation delay can be ordered 10 microseconds or even less actually. And this is has to do with just speed of light and physical distance. Those two servers are not very far away. And so your propagation delay is roughly like 10 microseconds. And so now if you look at this queuing delay of 40 microseconds, what we're saying is that the end-to-end packet delay in the context of a data center may be completely determined or dominated by queuing. That how much queuing you suffer is going to determine the latency or the performance you see. Is this argument clear to everyone? Okay, so what are we going to do about that? So you might also ask, who cares? 40 microseconds, you care. Because if all the statistics and the reports that we see, that latency matters hugely. So you'll see all these statistics. I'm never quite sure how they come up with them, but they do, and they report them, that like a millisecond, for example, in high frequency trading can cost you 100 million plus a month or something. And Akamai has this famous study that shows that if you have 100 millisecond delay in a page load time, that can lead to a 7% drop in conversion rates or sales. And so people really, really do want to get those latencies down. And you might think 100 milliseconds is a long way off from 40 microseconds. But then if you combine that with where we started, where we said one page load can result in 500 memcached lookups, for example, in the Facebook example, then that 40 microseconds added over, being accumulated over 500 memcached lookups or something, it starts to build up. So it actually matters in terms of revenue. But the other reason is also a perception. There is a lot of competition amongst cloud providers in terms of performance. And there are a lot of attention paid to the performance that they sustain. So if you look at headlines, you'll just see a number of these performance comparisons across clouds. And so people care about shaving off even a millisecond. And so then the problem is that if queuing delay dominates the end-to-end packet delay, TCP was really not your friend if you're trying to lower queuing delay. It's just not, it's actually designed in order to fill queues, right? We keep increasing your rate until that queue overflows. And this problem is actually made worse because of the typical flows that you see in data centers. So all the traffic measurements will show that most flows are short and latency sensitive. So this is something like a request response to a memcached lookup or so on. But there are also a number of flows that are really, really large. They're typically throughput sensitive more than latency sensitive. And this is, for example, copying your data over across servers or doing backups and so on. And so if you just ran TCP in a data center, what you'd have is that the elephant flows very quickly fill up these queues. And the mice flows that matter see these very high queuing delays. Okay, so this is the central problem that all of there's been a huge body of work trying to fix congestion control in data centers. And this is the key problem they're trying to solve. I'm debating whether to try and give you a quick sense of what people do in the remaining 4 minutes. So let me give you a very quick sense. We'll see how much of it sticks. If it doesn't, just try to get the main idea. So there's, again, two flavors of solutions. One is a more incremental one, and the other one is a more radical one. The more incremental one that came out of Albert Greenberg's group at Microsoft and some set of folks at Stanford is something called DC-TCP or data center TCP. And the basic idea is to use an old technique that we've talked about, which is explicit congestion notification, where a router is going to mark a packet if the packet arrived and the queue was building up. Right? We were using that in what we talked about in the advanced congestion control lecture in order to actually reduce that queuing delay. And so DC-TCP uses ECN. It has a few modifications that honestly you don't need to know, and I'm not going to go into them. It's really just making more aggressive use of ECN in order to keep the queue very, very small. What I want to talk about is how well does this do? And this is interesting because it gives you a sense of kind of how much performance TCP was leaving on the flow. And so the metric I'm going to look at here is flow completion time, which is measured from the time when the flow starts to when it's completely transferred at the receiver. Okay, that's flow completion time. We're going to compare it to an ideal flow completion time, which think of it just as a lower bound, right? Which is what is the best possible flow completion time you could have had if you were God and you had global view of exactly when each flow comes and exactly the state at each switch and router along the way. Don't worry about how it gets calculated. And so the metric that DC-TCP looks at is normalized flow completion time, which is the flow completion time you achieve compared to that ideal. So short way to think about it, mental model is how much slower am I than an ideal solution? And so this is the set of results that they discovered where, of course, if you're ideal, your normalized flow completion time is 1. So what this graph is showing is on the y-axis, the normalized flow completion time, which is how much better am I than an ideal solution. And they're showing that for increasing load on the x-axis. And what we see here is, if blue is ideal, it's 1. Yellow was TCP, which was pretty darn bad, actually. And then DC-TCP is a huge improvement. What it also shows us is if you're running your network at high load, so towards the right-hand side of the graph, you're still about 2 to 3x farther from optimal than one would have, or away from ideal. So there's room to improve things by that much. I'm now going to skip over the radical proposal, which was pfabric, which I'm going to summarize as being use priorities and give mice flows high priority and give elephant flows low priority, and just allow senders to just blast their traffic while setting that priority level based on how many bytes you had left to send. So mice get higher priority, elephants get lower priority. The main takeaway is if I go back to that graph, pfabric is this red line here, which tells us that this kind of more radical design, which involves changing both switches and encores in quite a dramatic way, could also give us pretty much close to optimal performance. I realize that was not an in-depth enough summary, but if the only point I would want you to retain is the question of queuing delay is the central problem when we're designing congestion control. And then ideas, there are ways, TCP is not good at eliminating queuing delay, or TCP is not your best friend if you're trying to reduce queuing delay. And there are solutions that have been worked on and have been proposed that do actually significantly reduce that queuing delay. If you're interested in more information about this, let me know and I will post links so you can read up more about them. So I'm going to skip this and just going straight to the summary. Data centers, new characteristics and goals. Some of them are liberating, like in particular having centralized control or single administrative control over the entire system. And others are constraining. In particular, this need to use commodity solutions so that we can scale is a major constraint. Scaling is the must. Performance is critically important. And some of the other things we talked about, like backward compatibility, heterogeneity, are somewhat less important. So with that, we're pretty much out of time. This is also my last live Zoom lecture that will release the live recording, the recordings for the review. So I just wanted to say thank you to everyone. I know this was not the dream semester, but thank you for sticking it out and helping us work our way through it. And I wish you all the best, both in wrapping up the semester as well as whatever your next steps are. Good luck to you all, and thank you.